Good morning. We've got our midterm coming up. We want to do some review here, and so we've got a set of these sampler problems. So let's go through them, and then along with going into some of the explanations on the examples that we have here, I will also try and point out review items that you want to be aware of. So on the practice set of problems for midterm 1, we've got a volume and a linear expansion coefficient. We've got a container of steel, and inside that container is carbon tetrachloride, which is a liquid. And what we have going on here is a volume expansion on the carbon tetrachloride and the steel. Now we're going to start with the container with the carbon tet inside at -10 Celsius, and then we're going to raise it to 80 Celsius. So the idea is that the container is completely full with an opening, I guess, an overflow opening. And when the temperature goes up, how much of the carbon tetrachloride is going to spill out of the container. So the idea on a problem like this is that we've got two different materials, and they're both undergoing thermal expansion. We want to be able to take the carbon tetrachloride and find out during that 90 Celsius temperature increase, how much of a volume increase will the carbon tetrachloride have, and then find out how much of a volume increase the steel will have. Now, the difference between that, if the steel and the carbon tetrachloride expand the same, if they have the same expansion coefficients, then we don't expect anything would spill out. But when we carry out these calculations, we find out that the carbon tetrachloride has an expansion coefficient, a thermal expansion coefficient, 581 parts per million. Now, that's a liquid. It tends to be larger than for a solid, something like steel, and sure enough, the steel expansion coefficient is given as the linear expansion coefficient, alpha, but we can easily multiply that by 3, and that will give us the three-dimensional volume coefficient. So that's what I've done here. And then we can do the quick comparison here of, hey, 581 is a bigger number than 33. The carbon tetrachloride is expanding by 15 or 20 times the rate that the steel is, and so there is going to be carbon tetrachloride overflow for the container. The container is listed as 200 liters. Both samples, the carbon tet and the steel, are having a delta T of 90 Celsius. And even though we're not using our 20 Celsius as a reference, these expansion coefficients are small enough that to a very good approximation, we're going to be fine. We could have done this in 2 steps. We could have done this at one step from -10 to 20, and then from 20 to 90, but this will introduce only a small amount of error into the calculation, so we're going to be fine. So I did carry out some extra significant figures just to make sure if we needed to be able to keep track of that. If there's a subtraction with the thermal expansion, then we're going to have to be prepared to be able to subtract a couple numbers. The numbers we got, the 10.458 liters, and then subtracting off the 0.594 liters leads us to 9.86 liters, and that's it. That's our answer. That's how much overflow we expect to have. So on this problem, the kind of things you want to be reviewing, review your thermal expansion formulas, both for linear expansion and for volume expansion. You could have a problem that could be one or the other, or something like this that involves both, and be really clear on a problem whether you need to do the problem in terms of linear expansion also. We saw examples back during lectures for this chapter where we did need to use, where we had volumes, but we could use linear expansions as a way of answering the questions about the volumes. Anyway, definitely thermal expansion. Now also in chapter 17, I guess this is kind of like a chapter 17 question, is the ideal gas law. So that's the other major topic there. And I think in these other practice problems, we're going to have plenty of chance to come back and look at examples of using that in other problems, probably down here with these PV diagrams and such. All right, problem 2 also, problem 1 didn't take up so much space. Problem 2 says that we've got a block of copper dropped into a large container of liquid nitrogen, and the liquid nitrogen is right at its vaporization point. It's at 77 kelvins. And so here is the container of N2, here is the temperature, 77 kelvins. Now if I drop something into the nitrogen, we're going to get vaporization. So what will happen is not a specific change, not a temperature change in the nitrogen, but instead we'll have a latent process. We'll have a phase change that takes place. And so for this, what we can do is find out how much heat is available in this block of copper. Now the copper is at 20 Celsius, which doesn't sound especially warm, a high temperature, until you realize the nitrogen's at 77. So as far as the nitrogen is concerned, the liquid nitrogen, this 20 Celsius, which I'm going to convert into 293, is a really large number. This sample of copper coming in is really hot as far as the liquid nitrogen is concerned. So the heat coming out of the copper, I can write that as it's a 1,000 gram sample. I'm writing down the specific heat, which was given, 385 joules per kilogram per Kelvin. And then the delta T, how much is the copper going to drop in temperature? Now, if this is a large container, which it says, of liquid nitrogen, the word large suggests to us that there's enough liquid nitrogen there that the liquid nitrogen temperature is pretty much going to stay right at 77. In fact, it will, because it's right at its vaporization point. So the copper is going to drop in temperature until it comes into equilibrium with the liquid nitrogen. And that's how we know that this is going to drop by 216 Kelvin, from 293 down to 77. All right, the thermal energy, the heat coming out of the copper, 83,190 joules. So that's an easy enough process to calculate here with the copper. Now, what I want to do is say that, well, the Q that comes out of the copper is the Q that's going to vaporize the nitrogen. So I can use the latent heat formula and flip the latent heat formula around, so I'm solving for mass. The mass of liquid nitrogen that vaporizes will be given by the amount of heat coming in divided by that latent heat number. Now the latent heat number is given as 201,000 joules per kilogram. And so I switched that over to 201 joules per gram and then divided and got 414 grams. So with these specific heat and latent heat problems, break them down into these individual steps where you're able to calculate, how much heat happened in this process, how much heat here, and then stop and be careful about which samples have heat leaving and which samples have heat coming in. So the problems are most easily solved just in terms of counting the amounts of heat and then keeping track of which direction they're going. The other item that came up here that I do want to point out, watch units. You know, some of these are going to be in joules, some could be in kilojoules. Some are in grams, some are in kilograms. Sometimes the specific heats are given in molar quantities. Sometimes it's so many joules per mole. So be careful, because you may need to add or take out a factor of 1,000 or something as you're carrying through the problem. So this is working out to 414 grams. Seems like a reasonable number, I guess, given the sizes of the samples that we're working from. Okay, questions on that? I'm going to go ahead and move on to the next sample. So this is coming from chapter 19, actually. I guess the next problem is maybe from 18. 19's got a lot of stuff in it, right? So 19's got the specific heats, the latent heats, and then it has the heat transfer methods, it has heat conduction. So there's a wide range of problems there. Make sure you're looking through homework problems as well. Remember the problems that we've set up here, it's just a few more additional problems. There's many more examples in the lectures and examples in the homework lists that you want to make sure that you're looking at. Moving on to problem 3 here. So this says that we have a 40 cubic meter sample of nitrogen. This is kind of a nitrogen exam maybe. Now this is nitrogen gas at 20 Celsius and 600 kilopascals of pressure. So that's, it's about 6 atmospheres, not quite 6 atmospheres. The problem asks us to calculate the RMS velocity. So there are formulas for that, and that should be doable. And then the average translational and rotational kinetic energies for the nitrogen molecules, and then how much total translation and rotational energy of the entire sample. Now that sounds like internal energy to me. If I'm adding together all of the kinetic energies, then that's really an internal energy question. So let's take a look at, well, I drew a picture here of what the sample might look like. I've got a volume which 40 cubic meters, so it's a good size volume, right? 40 cubic meters, every cubic meter is big, and I got 40 of those. The temperature we're working with is 293 kelvin, so I got that switched over, and then the pressure is at 600 kilopascals, and I got to watch for that factor of 1,000. Now, in the RMS formula, the VRMS formulas, we talked about this in lecture at some length. It's an easy enough looking formula, right? I mean, I just plugged the numbers in, but there's a lot more going on. You've got to be careful with units, and you've got to be careful with what the molar mass is going to be. So I'm going to use the formula which has big R in it. That's the one that I had suggested in lecture would be easier to work with. I'm going to go with that. I'm going to put in the factor of 3, put in R, and put in the temperature. So far, so good. But in the denominator, remember this is a molar mass, but that molar mass needs to be in standard units. And so I can't use grams per mole. I got to use kilograms per mole. So be clear with which formula you're using, and be clear with what the molar mass or the masses are going to be. So when I calculated all that, I ended up with a VRMS of 511 meters per second. Now I think this is even one of the examples that we had, during lecture that we had looked at, 511 meters per second at sort of room temperature nitrogen molecules. So if you're getting something, it's really easy. What happens on these types of problems is students get mixed up about what the masses are whether they're in kilograms or if you're using the Boltzmann constant formula, you have to make sure that the masses adjust for just one molecule. So watch for this. If your numbers are way off, if VRMS speeds that you're coming up with are really, really slow or really, really fast, go back and double check. Always ask yourself, does this make sense? You know, the numbers that I'm coming up with. Because that's the conceptual part of the course. If you come back and you say, well, sure, I was off by a factor of 100 trillion, but hey, it's just a formula and I just plug numbers in. We're building intuition about what range of values makes sense. So make sure you always ask yourself that question. Is this a reasonable answer that I'm ending up with? And if you get stuck, if you're taking an exam and you look at an answer and it seems like it's really too small or too large, write a quick comment. Write a comment saying, I think this is way too large than what I would have expected, but I just can't find my mistake. So if you write a comment or something, that lets me know you're thinking about this. You didn't just put down whatever number was in your calculator and move on. All right, on the second part, these nitrogen molecules that we're looking at, they want us to go in and determine average translational kinetic energy and average rotational. Now, we had looked at these and shown that the average kinetic energy of translation for a gas molecule is 3/2 kT, where little k is Boltzmann's constant, and since it's an average amount of energy per molecule, it's going to be tiny. This is going to be a really small number. And so I put in the 3/2, I put in Boltzmann's constant, which numerically is really small, 10 to the minus 23. And then the temperature has got to be kelvins here, because for these formulas, when the temperature goes to 0, it means that there's no kinetic energy. So kinetic energy and temperature have to line up with each other, where 0 temperature really means 0 kinetic energy. And so I've got to get that converted into kelvins. The number I ended up with was 6 times 10 to the minus 21 joules. Now, it's a tiny, tiny number, which is what it should be. It's just one molecule. One molecule of nitrogen is not going to have, a joule or 5 joules or 10 joules. It's, 10 to the minus 21 is an enormously tiny number, but it matches the fact that we're looking at individual atoms. For rotation, kind of the same thing. I have put in this factor of 2/2. That's often the way we think about it with the equipartition theorem. So 2/2 times k times the temperature, and that comes in at 4 times 10 to the minus 21. Now on C, since it's asking about the entire sample now what's going to happen is we're really working in terms of internal energy of the sample. And so I got to scale this thing up. Instead of looking at average kinetic energies, I can start counting how many moles I have and work in terms of 3/2 nRT. So I'm switching over to working in the number of moles of the entire sample and then using big R, the gas constant. That's 8.314. I didn't write it, Dad got it up here, I guess. So there it is written here. I didn't write down the details on this one, but we do want to make sure we get the temperatures again in kelvins. The number of moles here, I can calculate from PV over NR. So the number of moles worked out to be 9,852. It's a lot of moles, but it's a 40 cubic meter sample, right? And so here, I ended up with 36 megajoules and 24 megajoules. So those are pretty good sized numbers for the energies that we have here. All right, and as always, go through, check my numbers, make sure I haven't goofed up somewhere here, but that looks like question 3. Any questions that you guys have, let me know. Let's look at that last problem. So in this last example, this is a heat engine, and I know it's a heat engine because it's expanding at high pressure, drop, and then it compresses at low pressure. So if the general direction of this cycle is clockwise, then that's going to be a heat engine. If the arrows are reversed, then it's going to be a refrigerator or an air conditioner or a heat pump. That's going in the opposite direction. Now, the examples that we looked at in class were, I think, fairly challenging. We looked at the Carnot cycle, which is, you have to slow down and step your way through that. Same thing with the Otto cycle. The examples here, well, they're different. They've still got their own challenges and things you've got to be careful about. The diagram itself is just like a rectangle or a square on the diagram, and it consists of 2 constant pressures and 2 constant volume processes. Now, I wrote down a picture. I drew a picture of the cycle, drew my PV diagram, and then I wrote down the information that they told us, at least to start with. Now, the starting temperature was at 300 Kelvin, starting pressure was at 100 kilopascals, starting volume is at 1 liter. Now, that's 0.0010 cubic meters, so be careful again with factors of 1,000. There's a factor of a kilopascal, which is going to be a factor of 1,000 for us. Now, since we've got pressure and volume given at A, I can figure the pressures and volumes everywhere else, because I can see that, for example, point B is at the same volume as point A, but it's double the pressure. All the other points follow that same pattern. So I didn't make a table on this one, but I could actually go through and make a table of everything. So let's see. Temperatures would be handy to get written down also. So what I see, using the ideal gas law, I can see that from point A to B, for example, if the pressure doubles, volume stays the same, that means the temperature must have doubled also. So I'm using ratio representations from the ideal gas law in order to fit in what all of the rest of the temperatures are. Now, a couple of things I notice here is that it's always a factor of 2. Point A is at 300 Kelvin, and then up to 600, and then up to 1200, back down to 6, back down to 300. B and D are on the same isotherm. So B and D are the same temperature at those 2 points, although they have different volumes and different pressures. So as far as Q, W, delta E, and delta S. So Q. Q's not my favorite item to start with. I always tend to start with delta E. I'm going to do that first. So A to B, B to C, C to D, D to E. What happens along each step? Now, it says it's diatomic. Hey, it might be nitrogen, right? It was nitrogen in 2 other problems here. In any case, it's diatomic. And for a diatomic molecule, the specific heat at constant volume is 5/2, specific heat at constant pressure is 7/2. That's going to play into these QVs and QPs when I get to the heat. Since it's diatomic, the delta E's are just going to depend on 5/2 and delta T. It's always the same thing over and over. Delta E is just keeping track of how much energy has changed, and that's directly determined by the temperature. So these are all going to be the same formula, and that's why I like delta E's the best. And I went in and used those to determine I've got increases of 250 and 500, and then decreases of 500 and 250 joules. Now that makes sense because the temperature did that, right? It doubled, and then it halved and halved. And so the internal energy will follow that same pattern. And then at the end of the day, with internal energy, if I've closed the loop, the net internal energy difference is going to be zero. I'm going to be right back with the same internal energy that I started with. So internal energy doesn't depend on which path I take. If I can look at the endpoints, it's going to represent the same internal energy differences. Now, the next item I tend to look at, I guess, is work. I tend to leave heat for later. It doesn't make a big deal on this problem, but as far as work, with the volume, the constant volume process is A, B, and C, D. There's no area under that curve. We know that if there's no compression and no expansion taking place, that the work is going to be zero. So those are easy enough to write down as zero. Now, going from B to C is going to be pressure delta V. So the pressure here is two of those P naughts, which is 200 kilopascals. And then the volume difference is going to be the 0.001 cubic meters. And that left us with 200 joules. When I carried out the same calculation going from D to A, I got negative 100 joules. So that makes sense as far as area under the curve. There's 200 joules below the B to C curve, and there's negative 100 joules below the D to A curve. All right, now I'm getting net work out of this, right? Because I expanded at high pressure and got 200 joules, and then when I reset my heat engine, the pressure had dropped. And so I was able to push the heat engine piston back into place with only 100 joules of work. Okay, so I'm getting 100 joules net out of this each cycle. Now, as far as the Q's can be calculated a couple ways, and then we can double check. I'm going to go ahead and use the specific heat formulas. So for the Q's, at constant volume, specific heats are going to be 5/2 R. At constant pressure, they're going to be 7/2 R. And so putting the 5/2, 7/2, 5/2, 7/2, it alternates. I am putting in heat of 250 and 700. And that's kind of like the QH going in, right? That's the energy going into the system. And then here is the heat being exhausted. These are like the QLs. And it looks like the QH is 950 joules, and the QLs are 850 joules. And so the net here is I've put in 100 joules of heat. Now, the net from the heat in will match the net from the work coming out. Those are both going to be 100 joules. All right, what about the entropy differences along each path here? Well, for the entropies, what I can do is I can follow these definitions of Q for each of these steps. So the entropy formulas are going to look like the Q formulas, except that instead of a delta T, I'm going to have logarithms, natural logs of the ratio of the temperatures. So again, go back to the entropy formulas, which are dq over T. And from that, you can see that the T's have been factored out here, but in their place we have a dt over T, which ends up leaving us with a logarithm of T. Okay, so just carrying out the calculations there, 578 joules per Kelvin, when we're putting heat in, the entropies are positive. When we're taking heat out, the entropies are negative. Now, entropy changes are like the internal energy changes. They're state functions, and that means, but if I have a closed loop, where I bring the sample right back to the same pressure, same temperature, same volume, it's got to be the same entropy, right? So work and heat depend on which paths I take. Delta E's and delta S's do not. Okay, if I close the loop, those have got to zero out. And they did. So the two entropy increases we saw as the heat came in match the entropy decreases as the heat came out, even though the amounts of the heat weren't the same. So how efficient is this engine? We could ask that question. Well, we got 100 joules of work out, and the investment was 950 joules. So 10%, something like that, a little better than 10% efficiency that we have for the engine that we have outlined here. All right, so that's the first set of 4 problems. And if you guys have questions, stop by and we'll get those looked at. Let's see what the next set of problems look like. Ooh, these look like they're at least as challenging, maybe a bit more. So in problem 1, it says we have a closed steel container. The inner volume is 5.40 cubic meters. It contains 5 cubic meters of gasoline, and that's a misprint. I'm going to have to look at the solution to see what we are working with here. Okay, let me go back. I am going to have to double check this. If need be, I'll get these updated. Because it looks like the numbers aren't matching. Closed steel container 5.40, 5.00 cubic meters of gasoline, but only 0.1 cubic meter of nitrogen. I'm thinking those should match up. We'll see if we can figure it out from the answer here, but in any case, I'll need to go back and get this corrected. If the temperature of the container are going to go up to 60 Celsius, so I'm starting at 20, there's my gasoline, there's the nitrogen. What's going to happen to the volume of the container? What will happen to the volume of the gasoline? And what will be the pressure of the nitrogen? So let's take a look at this and see. First of all, I can start with the container. The expansion coefficient for the steel is 12.2, but remember, that's a linear expansion. To turn it into a volume expansion, I got to multiply by 3. So I turned it into a volume expansion by multiplying by 3, and that turned out to be 5.41. Now, I'm keeping way too many significant figures here, and that's because these expansion problems make me nervous. I know I'm going to be subtracting, and sometimes the differences are really small. So I did keep some extra significant figures. I don't think I need them in this example, but we'll see. We'll see what happens here. So the volume of the gasoline was listed as 5.00. And so same idea. I've got to pick up a volume expansion coefficient. Now this time it's 950 parts per million. So the gasoline expands a lot more than the steel. And I think we're fine with that. Let's see. So it started out at 5 cubic meters of gasoline, and there's a 40 kelvins increase, and so that's 5.190. So what's happened here is the steel has expanded a little bit, the gasoline's expanded a lot. The gasoline's taking up quite a bit of that space that used to be taken up by the nitrogen. Now, the steel and the gasoline are liquids and solids, and they're not very compressible. So if the gasoline's expanding and taking up more room inside, the nitrogen's going to get compressed. So that's what part C is asking about. What it's saying here is that the volume available to the nitrogen is now going to be 0.218 cubic meters. Whereas, here we go, here's our answer to, it's the simplest possible correction, I hope, is that the nitrogen is filling the remaining 0.4. That should be a 0.40. In fact, in the solution, that's what I've used. So I hope we've got that corrected. So the volume of the nitrogen is going to have to decrease from 0.4 cubic meters to 0.218, so it's about half the amount of volume that it used to have. And then the other thing happening is the nitrogen also is going to undergo this 40 Kelvin increase in temperature. And so I've used the ideal gas law as a ratio and said that PVT final equals P naught V naught over T naught initial, since they both equal N times R. And that allows me to write it in ratio form. So I'm going to say the pressure then is whatever the pressure started out, which was 1 atmosphere, and then I'm going to use the ratio of the volumes. Now, the reduction in volume is going to boost the pressure, and that's what this is showing. And also the temperature. There's a difference in temperature of 20% or so. And so overall, the effect is to increase the pressure on the nitrogen. I do like that problem. Again, this needed to be a correction here. That's 0.40 cubic meters. But I do like that problem. It's good, kind of overview as to what happens with gases compared with liquids and solids when we have these thermal expansion processes taking place. All right. Oh, and the problem also said neglect the vapor pressure of the gasoline. We're assuming that a negligible amount of the gasoline undergoes vaporization, that the vapor inside here is 100% nitrogen. Okay. All right. That all sounds pretty good. That was more challenging than it was on that other previous set. Problem 2 here says that we've got 100 grams of ice at negative 20 Celsius, and it's being added to 200 grams of water at 80 Celsius. And what will be the equilibrium temperature of the sample? At equilibrium, how much of this ice will remain, or will all the ice melt? And then it wants us to go in and do an entropy calculation for each component. So yeah, let's check this out. So in class, when we looked at a similar example like this, what we want to be able to do is break these processes down into individual steps and then do calculations on how much heat is entering or how much heat's leaving. Now, in this case, it's ice being added to pretty warm water. I'm going to say hot water. And so the hot water is going to be releasing or giving up or losing energy, and the ice is going to be gaining energy. Let's see if all the ice melts. So that first process would be to bring the ice to 0 Celsius. Now that's a specific process, and we're given specific heats of ice and water here that we can use. That required 4,020 joules. Let's see what happens when we take the water, the hot water, and bring that to 0 Celsius. Well, that's 200 grams in the specific heat of water times an 80-degree drop. That's 67,000 joules. So there's plenty of heat in this water to bring the ice up to 0 Celsius. Now the question is that 67,000 joules, is that enough also to melt the ice? And so ice melting to water at 0 Celsius, I can put in the mass of the ice, and I can put in the latent heat, and it says that melting process for the ice will require 33,300 joules. So now I've got to take a look at these Q's and say, look, how much heat do we have left over? Well, the water dropping in temperature here made available 67,000 joules. That's Q2. And then from that 67,000, I have used 4,000 to raise the temperature of the ice and 33,000 to melt the ice. I still have 29,600 and something joules available left over once we have melted all the ice. Now at this point, the ice sample and the water sample, they both consist of water at 0 Celsius. So it's fairly similar to that problem we looked at in lecture. So what we're left with here then is, I'm still using this formula and flipping it around. What we're going to do is take all of the remaining leftover heat, 29,656 joules, and we're going to treat the entire sample as one sample of water at 0 Celsius. And so now it's a total of 300 grams, and when I calculate how much I can raise the temperature with that amount of heat, it's 23.6 Celsius. So since we started at 0, that means the final temperature is 23.6 degrees Celsius, and we have melted all the ice. So the sample is 100% liquid water. If a question asks you that, if it says, what does the final sample consist of, remember to answer that question. So both answers are needed here. And I think, I'm hoping that one makes pretty good sense. How did that go, manipulating those different samples? All right, let's move on and take a look at problem number 3. Now, I ended up making a few corrections on this solution. So again, if you find problems anywhere, let me know. I can get these updated, or I can rewrite them if needed. On problem 3, it says that we have a storage tank of 55 kilograms of nitrogen at a pretty high pressure. You know, that looks like 22 atmospheres. And a temperature of, it's just room temperature. So this sounds kind of like problem 3 from the other page. Calculate the translational internal energy of the nitrogen sample. Calculate the rotational portion of that. Calculate the translational internal energy, the rotational internal energy. Those combined would be the total internal energy. And then find the RMS velocity. The temperature of the sample is raised to 75. Go back and recalculate everything. So yeah, it actually does address some of the same questions. So that's fine. We'll get a chance to go in and try this out. Now, the mass of the nitrogen, 55,000 grams, pressure, temperature, and I got the temperature converted into kelvins. I want to find out how many moles I've got. So they told me how many grams of nitrogen, and that's sensible. But for the formulas I'm going to be using, I want to know how many moles. So it turns out that we have a sample of 1,964 moles of nitrogen, and I'm starting to think was that the same number of moles? It was kind of the same thing, right? Like a couple thousand moles of nitrogen in that 40 cubic meter sample that we looked at. This one's under much higher pressure than the other example. Now the translational internal energy is 3/2 nRT, and the temperature it's in Kelvin. I got that converted. Got to check all my units, make sure I have the right number of moles, but that's giving us 7,176 kilojoules. Actually, that was 1,000, so I used kilojoules instead of joules on that. I did solve for the volume here. I'm just curious. I guess I just did that out of curiosity. It's at 2.2 cubic meters. Then if we do the energy of rotation, this is nRT. Energy of rotation then is 4784 kilojoules again. Now when we get to the RMS velocities. So for the RMS velocities, I'm going to go back and use the easier formula. Oh, look at that, it is the same. We're at the same temperature. We're at 20 Celsius or 293 kelvins. So the VRMS is the same calculation. It's nitrogen again. I do like using nitrogen as a sample because, 70% of the air is is nitrogen, and so 71%, something like that, or 78%, right? So a good portion of the atmosphere is nitrogen, and that's a common material around us all the time. So for me, that means I can kind of imagine, oh yeah, I can see all those nitrogen molecules moving around in the air at those speeds. Now, the last portion of this was change the temperature and go back and recalculate everything. So, the internal energy calculations are just going to scale according to the temperature increase. They're going to both go up. Now, in Celsius terms, it seems like the temperature went way up, right? It went from 20 to 75. But before you start thinking that's a factor of 4 increase, it's not. Because in temperature, if we want to think in terms of ratios, we really have to think in terms of kelvins. And so the Kelvin temperature went from 293 to 348, and that was a much more modest increase. That's what, a 20-25% increase. And so that's what we're seeing in the internal energies. They're going up by 20-25%. Now also with the VRMS, as the temperature goes up, that means the molecules are going faster, but this formula is square rooted too. So again, it's not as dramatic as one might think looking at the 20 Celsius and 75 Celsius numbers. Okay. All right, so that looks good, that all looks good. Let's move on to this last problem. Now this is another thermodynamic cycle, and there's a pretty good chance there's going to be one in the midterm, right? We looked at some in lecture, the book goes over these, and now in review we're looking at these too. And so what this is saying is that, oh look, it's oxygen, and it's O2, oxygen is O2 and it's diatomic. It's taken through this thermodynamic cycle in the diagram. Our starting temperature at A is 250 Kelvin, so it's a little chilly. Calculate the temperatures at B and C. How many grams of oxygen are in the sample? And calculate delta E, delta S, calculate W and Q. So very much the same list of questions, and not surprising, we said that analyzing these thermodynamic cycles is one of our real emphases in these chapters, and being able to just go in and solve for everything, right? What happened at each step along the way. Now this has this added feature, I guess, of saying that they want us to go in and calculate how many grams of oxygen. Now the molar mass for oxygen is 32 grams per mole, so we got to keep an eye on that. Now also what was down here at the bottom, which I had missed up until right now, is that the pressure is at 200 kilopascals and the volume is at 1.20 cubic meters, and I am assuming that's at point A. So I think the subscripts dropped off somewhere on that. That's at point A. And so when we come up to part A here, the temperature at point A is 250 kelvins. Now in going from A to B, the pressure tripled, volume stayed the same. So the temperature should go up by a factor of 3, and that puts us at 750. And going from A to C, oh, the volume tripled also, but this time the pressure stayed the same. It's going to give us the same temperature. So this always seems to happen. We'll have to write a problem maybe on the midterm where it doesn't, but B and C are at the same temperature. And so they're both on the same isotherm. Now, that path on that diagram, that is not an isotherm because it's not curved. So that is a straight line path between B and C, and that means that the temperature actually is going to go up a little bit at the middle and then drop back down by the time it gets to C. So don't assume that's an isotherm. It's not. Now, getting on to, well, we got the temperatures figured out. Getting on to the number of moles, PV over RT, and again, these are the starting pressures and volumes. And so I'm going to plug those in. Everything looks good. I've got temperature in kelvins, and I ended up with 115 moles as the sample size. If I want to find out how much mass, I can take that number of moles, multiply by the molar mass, and that gave me 3680 grams of oxygen. Okay, so we got 3.7 kilograms of oxygen in the sample. What was the volume again? 1.2. Okay, so 1.20 meters. It's not an enormous size. It's under a couple of atmospheres of pressure. But notice that we have several. And it's at 250 kelvins. So 250 kelvins is going to make a difference here too. The molecules are not moving especially fast, and yet they're able to maintain the pressure. That means there's got to be more of them in the sample. So that 3680 grams of the O2 is our mass calculation. Okay, finally, D and E solve for everything. So you guys remember, I like delta E internal the best. This is oxygen, it's diatomic. And so I'm just going to use 5 halves NR delta T all the way through. And that gave me, there's only 3 steps, 1.20 megajoules. From B to C was 0. So the internal energy at C matches the internal energy at B, even though at the midpoint, along the way, not just the midpoint, but all along the way, the temperature went up a little bit, and then it came back down a little bit. Okay. So, but overall, that path going from B to C, we ended up at the same temperature and the same internal energy. And then from C to A, we lose the energy back that we had gained. And so, again, it's a closed cycle. And since it's a closed cycle, delta E for the entire closed process should add up to be 0. That's something you can check when you're doing these problems. Let's see, what's the next best thing? Delta S is hard. I'm going to go drop down here and do work. A to B is constant volume. If it's constant volume, it's 0 work, so there was no energy brought in through work during that process. Now, for the work from B to C, I can't use the isotherm formula. It's approximately right, but it's going to be a little bit lower. The work we have here is more than the isotherm formula would tell us, because again, we have a straight path here, whereas the isotherm would dip, and that straight path is going to have more area under the curve. Now, in this problem, I can just use area under the curve to go in and solve what's going on here. So let's see, what do we have in terms of area under the curve? If I look at the area under, let's do this. Let's do C to A first. If I look at C to A, what I have underneath there is the height of that rectangle is P naught, and the width is 2 volumes. And so that would be 3 P naught V naughts, or 2 P naught V naughts, sorry. Now, in addition, oh, here we go. I did do this up here. So I've got the area under here, which is 2 of those squares. And then I have another square in here, and then if I take those 2 triangles, those are going to give me 1 square. So I have the equivalent of 4 squares, where each square is V naught, P naught, and that's what I did. So again, I'm using area under the curve, and that gave me a value of 0.960 megajoules. Now when I come down to C back to A, now that I've done that calculation for B to C, I can see that C to A is going to be half that amount, and that's going to be 0.48 megajoules. So adding up all the work, it looks like the work overall was 0.480 megajoules. We did get net work out of our heat engine, which is what should be happening for a heat engine. Let's see. On the Q side here, calculating the Qs, I'm going to get 5/2 nR delta T because this is a constant volume process. I am going to get 7/2 nR delta T here for C to A because it is constant pressure. But what am I going to get for Q from B? Did I not? I never put an answer in. Oh no. Why did I do that? I guess I was going to come back and put that in, but I don't think, I think I forgot. I'm going to definitely lose points for that. All right, how are we going to get Q for B to C? Because it's not one of the processes that we talked about in class. We don't have a formula for that particular kind of path. What we can do is this. To calculate the Q from B to C, what we can take a look at is how much change was there in the internal energy, and the internal energy didn't change along that path. So I know that the overall internal energy did not change, and that means that QBC will be equal to WBC. So that's what it is. It's the 0.960. I am sorry I left that out. That's crazy. Okay. Yeah, I have to go back and remember to write that back in. All right, so we got the Q's, we got the W's, we got the delta E's. Ooh, it's the delta S's. These are, I think they're fun, but I do have to slow down when I do these so that I am getting the right answers in. For delta SAB and delta SCA, those are well-defined processes. What I mean is we've looked at them before. This is constant volume, this is constant pressure, and I can use the formulas for specific, molar-specific heats for those. And so I got 2.64 of an increase going from A to B. That's where the heat's going in, right? Yes, that's where the heat goes in. B to C is also where more heat goes in. And then C to A is where the heat comes out. So heat goes in, that gave me 2.64. I'm going to leave BC alone. BC adds a lot of complexity here, right? From C to A, this is where the heat's leaving, negative 3.69. Now, for B to C, how are we going to work the entropy here? Because entropy, I could think of it as Q over T, but the T's not constant along that path. So what we could do is, and we used this very same trick in lecture when we took a look at a very similar problem in chapter 20, an example in lecture, where we said, look, it doesn't matter how I get from B to C, whichever path I take is going to give me the same answer. So the first thing we could do is just say it's got to be whatever makes sure that the entropies all add up to be 0. Whatever it takes to get the entropies to add up to 0, that's what I'm going to put in, 1.05. Now there's a way we could double check that, and we could double check it by saying, an isotherm process would also take us through B and C. And so I could take the Q for that process and divide out the T. Now the Q for that process, for an isotherm, is nRT ln of VB over VC, or VC over VB. That's the work formula and the Q formula for an isothermal process. So putting the numbers in, sure enough, I get the same answer. So we kind of checked that two different ways. We used an isothermal path, which will work. All I need to do is get the correct endpoints to get the right answer. And then we also just used the argument that all the closed process, all the delta S's combined to give us no net entropy change. So that seemed to work too. All right. So I hope that was useful. I know the keys are already out there in the questions, but sometimes I feel like just going through this together and kind of talking about it can really help. So I hope you guys, the midterm is coming up, not too far from this, and I hope you guys are prepared. If you've got any questions, hop on over into office hours and we will get those looked at.